Let's start simple. Okay, so what makes the V8 engine such a legend? Why has this design survived for over a century while countless other engine layouts faded into obscurity? Well, it starts with a surprisingly simple idea. A V8 engine uses 8 cylinders split into 2 banks arranged in a V shape around a single crankshaft. Sounds straightforward, right? But that layout accidentally hits one of engineering's sweet spots. Think about it. Engine designers are constantly fighting a three-way battle between power, reliability, and complexity. More power usually means more stress. More reliability often means sacrificing performance, and reducing complexity can limit both. But the V8? It manages to balance all three. With 8 cylinders firing in sequence, a V8 can produce strong, smooth, and consistent power. At the same time, the design is robust enough to survive years of abuse, whether it's hauling heavy loads, powering a performance car around a racetrack, or even driving a boat across open water. And here's where things get interesting. Because engineers have spent decades perfecting the V8, manufacturers know exactly how to build them, mechanics know exactly how to repair them, and enthusiasts know exactly how to modify them. It's an engine architecture with over 100 years of real-world testing behind it. That's why you'll find V8s everywhere, from muscle cars like the Ford Mustang to heavy-duty trucks to marine engines, and even some experimental aircraft projects. So the secret of the V8 isn't that it's the most powerful engine ever made. It's that it strikes an incredible balance between power, durability, cost, and simplicity. And in engineering, finding that kind of balance is often what turns a good design into a legendary one. So why would anyone even consider a W9 over a V8? Let's break it down. So what exactly is a W9 engine? It's what happens when an engineer looks at a perfectly good V engine and says, no, not enough cylinders arguing with each other. But surprisingly, it's a real concept. Every time you add another bank, the CAD software develops a new anxiety disorder. Picture this, instead of arranging cylinders in a straight line like an inline engine, or splitting them into 2 banks like a V8, a W9 uses 3 separate cylinder banks. 9 cylinders, 3 banks, all connected to a single crankshaft. Viewed from the front, the layout forms a literal W shape. The W9 actually solves several engineering problems in a surprisingly clever way. Let's start with packaging. Now, when most people think about engines, they think about horsepower, torque, or maybe fuel economy. But engineers? Engineers obsess over space. Every centimeter inside a vehicle is fighting for survival. The engine wants space. The transmission wants space. Cooling systems want space. Passengers want space. And somehow, all of that has to fit inside one machine. The engine can potentially be made significantly shorter than an equivalent V8. Think of it like packing luggage. A V8 lays everything out in 2 rows. A W9 starts stacking things inward. Same amount of space being used, but used differently. More cylinders, less length. And in engineering, saving length is a big deal. In a mid-engine sports car, even a small reduction in engine length can improve weight distribution, handling balance, and packaging flexibility. The entire vehicle can be designed differently simply because the engine occupies less space. But cars aren't the only place this matters. Take aviation. Aircraft designers are constantly fighting drag. The smaller and cleaner you can make the engine installation, the better. A shorter engine can mean a slimmer fuselage, tighter engine nacelles, and cleaner airflow around the aircraft. Less drag, more efficiency, better performance. So the W9 is doing something unusual. It's spending mechanical complexity to buy back space. And sometimes that trade is worth making. But packaging is only the beginning, because there's another advantage hiding inside those 9 cylinders: smoothness. And this is where things get surprisingly mathematical. Every engine produces power in pulses. A cylinder fires, power is produced. Then the crankshaft rotates until the next cylinder fires. The question isn't whether power comes in pulses. The question is how close together those pulses are. The more cylinders you have, the more frequently combustion events occur. And that means the individual power pulses become smaller, closer together, and more overlapped. A V8 already does this pretty well, but a W9 pushes it even further. Instead of feeling distinct pulses of power, the engine begins producing something closer to a continuous stream of torque. The result? Less vibration, less harshness, less mechanical stress, and a smoother overall driving experience. That's valuable in luxury vehicles where refinement matters. It's valuable in generators where stable rotation improves electrical output. And it's valuable in aircraft where reducing vibration can increase structural life and improve passenger comfort. In other words, adding cylinders isn't just about making more power. Sometimes it's about making power feel invisible. But then we arrive at what may be the W9's biggest theoretical advantage: power density. Because every cylinder is essentially another opportunity to produce energy. More cylinders mean more combustion events per revolution. More combustion events mean more potential power output from the same engine volume. And that creates two possible outcomes. Option 1, make more power than a similarly sized V8. Option 2, make the same power while running at lower RPM. And that second option is incredibly important because high RPM is expensive, not financially, mechanically. As RPM rises, piston speeds increase, bearing loads increase, valve train stress increases, friction increases. Everything inside the engine starts working harder. But if a W9 can achieve the same power output at lower RPM, all of those stresses can potentially be reduced. The workload gets distributed across more cylinders. Each piston does less work. Each connecting rod sees less stress. Each combustion event contributes a smaller piece to the overall power output. In theory, that could mean improved durability, smoother operation, and better efficiency, especially in applications where engines spend hours running at a constant speed. Things like generators, aircraft, industrial power systems, the kind of machines where reliability matters just as much as power. Of course, there's a catch. Actually, several catches. Okay, so if the W9 is so compact, so smooth, and theoretically so brilliant, why aren't they everywhere? Why isn't every supercar, aircraft, generator, and questionable Facebook Marketplace project powered by a screaming 9-cylinder mechanical abomination? Because reality showed up, and reality was not impressed. See, the W9 suffers from a condition engineers refer to as sounding amazing in a patent drawing. The first problem is cooling, specifically the middle cylinder bank, because somebody looked at 3 cylinder banks packed together and apparently forgot that engines get hot. The outer banks can at least see daylight. They get airflow, they get cooling. The center bank? The center bank gets trapped between 2 giant heat-producing neighbors and spends its entire life being slow-cooked. It's basically the middle seat on a long-haul flight, except the people on both sides are on fire. Heat gets trapped, temperatures climb. Cooling systems start filing complaints with management. And once temperatures start rising, everything gets worse. Oil breaks down faster. Components expand. Clearances change. Combustion becomes less predictable. Eventually, the engine starts asking difficult questions like, would you like detonation with that? And nobody wants detonation, unless you're building artillery. Then there's the exhaust. Now, normally, exhaust routing is annoying, but manageable. A W9 takes that annoyance and promotes it to upper management. The outer banks are fine. The middle bank, however, is buried deep inside the engine, like someone hid an entire exhaust system in a puzzle box. Getting headers, manifolds, turbo plumbing, heat shielding, and maintenance access all working together becomes an exercise in creative suffering. Every pipe wants to occupy the same space. Every component is in the way of another component, and every engineer involved develops a new respect for aspirin. But the real nightmare begins when we talk about balance, because engines don't just make power. They shake. Every piston moving up creates forces. Every piston moving down creates forces. The trick is arranging those forces so they cancel each other out. A V8 does this reasonably well. An inline-6 does it beautifully. A W9 has 9 cylinders. And 9 is an odd number, which sounds harmless until you realize engine balance is basically mechanical symmetry, and odd numbers are not particularly interested in symmetry. The forces don't naturally line up. The firing events don't distribute as cleanly. Vibrations show up in places you'd rather they didn't. And those vibrations don't just affect comfort, they affect durability. Bearings see more load. Crankshafts experience more stress. Components fatigue faster. It's like having a tiny earthquake living inside your engine block. All day. Every day. Now compare that to something like a W12 or W16. Those engines are still complicated. Ridiculously complicated. But they're complicated in a way that's mathematically cooperative. Their cylinder counts allow much more symmetrical firing patterns and better inherent balance. The W9 doesn't get that luxury. It has to fight physics every step of the way. And unfortunately, physics usually wins. Then we get to the crankshaft. Remember how a V8 crankshaft is already one of the most heavily engineered components in an engine? Good. Now imagine explaining to that crankshaft that it's responsible for coordinating 9 cylinders across 3 banks. The crankshaft immediately resigns because now it has to deal with unusual bank angles, complex firing intervals, balancing requirements, and enough custom geometry to make a CNC machine question its life choices. And that complexity spreads everywhere. More camshafts, more timing components, more synchronization, more opportunities for something expensive to happen. Every additional part becomes another thing that can wear out, fail, leak, loosen, break, or decide it no longer wishes to participate in the combustion process. And then we arrive at everyone's favorite engineering problem: money. Because all of this complexity isn't free. A V8 benefits from over a century of development. Parts are everywhere. Mechanics know them. Manufacturers know them. Tooling exists. Supply chains exist. Entire industries exist. A W9 gets none of that. Almost everything would need to be custom. Custom crankshaft, custom engine block, custom cooling system, custom exhaust, custom tooling, custom headaches, and custom prices. Building one is expensive. Maintaining one is expensive. Repairing one is expensive. Even finding somebody willing to work on one might require bribery, which ultimately explains why the W9 never became mainstream. It's not because engineers couldn't build one. They could. Some actually did. It's because every advantage came attached to a stack of engineering problems tall enough to blot out the sun. The W9 is what happens when engineers ask, "Can we do this?" And the answer is yes, followed immediately by, "But should we?" And for most manufacturers, the answer to that second question was a very polite, very expensive, and very firm no. In the end, the W9 becomes one of those engineering ideas that lives in the category of, "Yeah, we could do that," and then immediately followed by, "But absolutely nobody is paying for it." Because that's what the W9 really is. A fascinating what-if engine layout in automotive history. It proved something important. Unconventional engine architectures aren't just theory. You can physically build them. You can get them to run. You can make 9 cylinders cooperate in a 3-bank W configuration without the universe immediately collapsing. But it also proved something else. Just because you can build it doesn't mean you should mass produce it. And that's where reality steps in. Because manufacturers didn't stick with V8s, V10s, or flat engines by accident. They stuck with them because they work. They're predictable. They're affordable. They're easy to service. And more importantly, they scale. A V8 isn't just an engine anymore. It's an ecosystem. Look at something like the Ford Mustang GT or the Chevrolet Corvette. These aren't just performance cars powered by a V8. They're the result of decades of refinement, tooling, manufacturing efficiency, parts availability, and real-world testing across millions of engines. That's not just engineering. That's industrial momentum, and the W9 doesn't have that. Not even close. So in the real world, today the V8 wins. Not because it's the most advanced concept on paper, but because it's the most complete package in reality. But, and this is where it gets interesting, that doesn't mean the W9 is worse engineering. It just exists in a different category. Because if you zoom out far enough, the W9 isn't really trying to compete with the V8. It's exploring a different design philosophy entirely, one focused on compactness, higher power density, smoother torque delivery, and extracting more performance from less physical space. And that idea is not new. We already see it in things like multi-bank engines, including designs like the W12, where packaging and smoothness start to matter just as much as raw simplicity. Now take that idea and push it further. In environments where space is limited, vibration is a serious problem, and continuous power output matters more than cost or simplicity. Things like aircraft systems, high-efficiency generators, or experimental propulsion platforms, the W9 starts to look a lot less weird and a lot more intentional. Because suddenly, complexity isn't a flaw. It's the price you pay for optimization. So here's the real takeaway. The V8 wins the present because it's proven, because it's accessible, because it's everywhere. But the W9? The W9 is something else. It's a direction, a reminder that engine design doesn't have to stop at what's practical today. It can push toward what's physically possible tomorrow. And maybe one day, when manufacturing catches up and complexity becomes less of a limitation, we might look back at the W9 not as a failed idea, but as an early sketch of what ultra-compact high-performance engines were always trying to become.